over here for the last minutes.
Yes.
And we just say like sound.
Yeah, it's
You should have found it, okay. We did it.
are we for audience?
Yeah, sure.
Okay. That's
Sarah, what your job in social?
no, that's the yeah, the two comments. Yeah.
I don't know if it's so. Yes, it's talks, we may have in terms.
What we can do is
And my colleague had.
I read since friends.
Whether I can also work.
Who you're working with?
How much it is?
Well, don't know. So
It's like a separation band.
yeah,
So they're
it's
people-
not free to go to the second floor and to get somebody. Yeah. Secretary gives them all the go.
Yes, so loud. I tried.
But you should have it the same key.
Like, the other floor, we made it, like.
But not-
We can send it out upstairs.
Because you get that now, but it was the
They're not that bad. There are several people that need to do it.
Mhm. There's more astronomy and sciences. I can see.
Get rid of those messages.
Right.
They won't read them.
Yeah, it's.
Did I use screen?
You can't see it.
I can't see what is there. Turn up one, get that volume there.
I can see that. It's come for me. It's come for me. Yep. I don't know. Is it?
You don't have the messages.
You could see a movie.
Screens. Sorry, we just want to make sure we're showing on Zoom the right thing. Yes. Okay, we got it. Great, thank you very much for your patience, and it's a great pleasure to introduce Krisztián Vida here from Konkoly Observatory in Hungary. As you probably know, this year with the NEO school that's taking place, actually just started yesterday instead of it going 2 weeks, but only 2 days here today. So he's one of the tutors at the school, and he'll be telling us today about flares and coronal mass ejections and on stars. So, oh, I should say, sorry, I forgot. Krisztián Vida got his PhD in 2010 at Erasmus University, and since then has been at the same place and is now a research staff at the same. So, thank you very much, and we'll begin.
Thank you for the introduction. I listed all the important logos and whatever that's needed this week. So read it fast because it might change by the time you finish it. So the situation in Hungary is probably a bit similar to Greece in terms of research funding and the government's interest in research funding. So it's not that great, but we are still alive. Anyway, so today's topic is flares and coronal mass ejections on pulsars. So the first question is, how many of you are doing stellar research here?
For some.
Some, it's close enough. So you know flares. So you understand the title. That's a good start. Let's see. Right. So first we are going to deal with CMEs on M-dwarfs because, well, that's probably the most interesting or general topic. Why do we care of the whole thing? So if you try to do some outreach or general introduction thing, you first explain the habitable zone. So if you want to explain the habitable zone, you need the definition, you go to Wikipedia and copy that paragraph. So basically the habitable zone from the most basic definition is basically the zone around the star where the water can remain in a liquid form, right? It's easy. Everybody can understand it, even small kids from kindergarten or primary school, right? So habitable zone, check. But is it really all what we need for life? Probably not. The distance is not enough for having water in liquid form either. So you need probably an atmosphere for life and for water as well to remain there. You need a star that's friendly to life. In several ways, we are going to see that. So as Heidi mentioned once, that who is organizing the NEO school, that radiation is good for life because it helps you to evolve on a long term. So in short term, you get skin cancer. On midterm, you get birth defects and stuff like that. But on a long term, if you get just the right amount of radiation for a very large number of very unhealthy and sick horses, you might get one Pegasus or unicorn or one of the fancy stuffs. So on the long term, it might have the evolution of life if you get the right amount of radiation. If you get too much, it destroys all. If you get nothing, then it's not really helpful. If you get too much of the stellar activity, it might destroy actually the atmospheres by just wiping off the atmosphere with that. So you don't want that, or you may want that, but that's a bit different topic. I think I might get into that a bit later. So stellar CMEs are hard to detect. So in the case of the sun, it's easy because you just look up and it's there. If you want to do detailed study, you go there with a bucket and take a sample of the material, and then you can just analyze it in the lab. You don't tell that to solar physicists because they get very angry because it's not that easy. It needs complicated satellites and stuff. But in theory, you can easily do that. In the case of stars, you can't go there because it's several light years away. So it's impossible, not just in the near future, but basically in general, to go there. So you can't take any samples, it's far away, there's not enough signal. They are random events, so if you want to study them and you want to go to a big telescope and say you want, well, 3 weeks of observing time because you have no idea when it's going to happen, and you will probably get a message that's basically rejection and just shoo you away from the telescope time because they all the telescope allocation committees want these big results. That's guaranteed. And with random events, you are getting hard times. As far as we know, they are mostly found on M-dwarfs. We are going to see that, and their typical velocity is a few 100 kilometers per second, and dedicated observations can be really useful. So let's see the details, how we got these conclusions. So flares are basically easy on the sun and on the stars as well. So on the sun, you can see that it's brightening up, and you can see the same thing on other stars. So flares are very typical light curve shape with a sudden brightening and the decay phase. What's happening here is that the surface magnetic field quickly rearranges, and this goes with the sudden energy release. And in the case if some material is trapped inside the magnetic field, it can be ejected towards the into the interplanetary space. In the case of the Earth or other planets, it can cause aurora and I already told what can happen in other stuff when you have energetic events. There are different methods that can be used to trace these events. There are a number of detections in X-rays, just a handful. No luck in the radio regime at this point. So Jackie Williamson in the US basically wrote a 200-page long PhD thesis of the years of struggle where she wanted to find CMEs in radio without luck. This year and last year's latest results is that there might be some detection in the low power in radio. So that's a strong maybe for the radio regime. So most of the detections that we currently have are in the optical regime, so visible and Balmer lines. So what you see in this case is basically that you have the H-alpha line, and then the material is coming from the star towards the observer. Then in a very lucky case, you can see small bump, which is basically a tiny emission feature that is coming towards you and causes a Doppler shift in the Balmer line. And this event shown here is a very lucky series of observations on the V374 Pegasus star, which is a small M-dwarf that's rotating very fast with a very active magnetic field. And it was there by accident. So it was observed for a science paper. It was one of the first, or maybe the first, ZVI map on a small star. He found that the magnetic field is very stable, so it's not changing over a year. And then they left all the data in the archives and didn't care too much about the H-alpha line. So we were observing the star for completely other reasons. And I had the idea to check the archives if they have some high resolution spectra, which they have. And we found the CME events, which turned out to be the best observed CMEs basically ever. So quite lucky incident. And this is the only case where you have an idea, maybe not been made, but this was for a long time the only case where you had any idea about the surrounding magnetic field and also the surface magnetic field, so the surface of configuration, because we know that the surface is very stable, at least on the year from the ZDI maps. And from photometry, we know that the surface spots are stable for 15 years or so. So there is not that much change there either. So from these events, you could find out that the escape velocity is roughly 600 kilometers per second. So the first two events, their projected velocity is just below it. So whatever came out probably fall back on the star surface, but the third event left the star. So it's about 600 kilometers per second. So that's a successful CME. And that's basically the only one where you can compare the results with photometry and the magnetic field structure. So the colleagues in Austria could make some more detailed models. The question arose, if there is one such nice event in the archive, maybe there is more. So we went and searched for the virtual observatory archive to see what's out there. So in the end, we found 400 late type M-dwarfs with different, actually not that lucky series of observations. So this was the only case where they were really focused to get the science paper out. So they used the best telescope, the old instrument station, they have lots of observations, and the other were just some follow-up stuff. So not that detailed observations, unluckily for us. But in the end, we checked more than 5,000 spectra. So if you just want to observe that, it's insanely long time. So you basically, it's basically impossible to do. More than 1,000 hours of observation. We checked for the H alpha, H beta, and H gamma lines. Visually, we check for any asymmetries. It takes more than weeks to go through all the data, and it's very boring. But from all these, we found 500 such spectra from 25 objects with 9 larger events. But still, the original event that started the whole idea was still the best one. And for the first time, we have enough data for doing statistics. So what can we find from these? So you do some statistical magic, principal component analysis, which is basically you take all the data that you have, the multi-dimensional space, and try to rotate it in a way that reuses the dimension to a way that you can handle and see the actual information more easily. The drawback is that in this case, the axis of your new dimensions are not necessarily making any sense in a physical way, but yeah, you manage to reduce the dimensions. And usually you can find out that even if you start with, I don't know, 100 different parameters, there is maybe 10 the axis that actually contains information if you combine them. So first of all, we find the obvious information that smaller stars are cooler. Yeah, we know that from high school basically, so that's no news. Fast rotating stars are more active. Yeah, thank you. We already knew that. Activity indicators are correlated. Of course they are. But the interesting thing is that here you can see some interesting things. Basically, you can see that the stars with stronger magnetic fields produce more CMEs, which is something that sounds obvious, right? If a star is more active, produces more flares that we know, and it should probably produce more CMEs as well, right? Because the sun, we know that basically every larger flare is followed by a CME, so this must be probably the case on other stars. But there are some theories that maybe the very strong magnetic fields could block the ejection of the CMEs. So yeah, it seems obvious, but it's not really. so obvious. If we go for checking the typical velocity of the masses, we see that typical velocities are something like 100, 300 kilometers per second, which are surprisingly mostly below the typical escape velocity. So most of the events are unsuccessful CMEs. There is some debate in the field that we should even call these CMEs or find some other names like coronal evaporations or whatever else. The thing is that the typical velocities we find is the typical observed velocities. So there might be some projection effects playing in. So it's possible that the actual velocities are higher, and we only observe the Balmer lines, which means that we might be actually seeing just the initial speed of the event. And when the material is ejected and comes out from the star, slowly cools down. And it is possible that we know on the sun that it's continuously, so the speed is continuously increasing. So even if it starts with a few hundred kilometers per second, it will end up with 1,000 or 1,500 or so. But maybe we can't see that because it can't be seen anymore in the Balmer labs. So we have no idea because that's the only measurements that we have. So we can just make educated or best educated guesses. Yeah, so that's basically what I just told. So it's possible that it's accelerated further, and by the time it reaches the it reaches higher, maybe the escape velocity is different. Yeah, but these are just basically guesses. So what's the case in the case of solar-like stars? So these were only the case of M-dwarfs. So if we do the same experiment on solar-like stars and go for air hives, check for all the observations of solar-like stars, we could gather more than 3,000 hours of spectra and find no CMEs at all. So what's happening here? So there might be a few explanations. It's possible that there are no CMEs at all on solar-like stars. Maybe they are too small to be observed. Maybe it's blocked by the strong magnetic field. Maybe we are using the wrong technique. So maybe the Balmer line is not suitable to do that. We have no idea. But if we extrapolate the solar activity so just scale up to these stars, we should see some events here with this number of observations. But it's also possible that this scaling up simply doesn't work. And then we are out of luck. So what did we learn until now? We know that on the sun, depending on the activity cycle, we can see roughly 4.5 to 6 CMEs per day. So on other stars, this is basically impossible to see. So if we just find one event, we are already happy. We know that on the sun, basically every strong flare is followed by a CME. And from the virtual observatory data, we can find that we see rates something like 1 to 20 events per day for the late time course, which is a bit lower than the scale of solar case. So what are the possibilities? The scaling law doesn't work. We are looking the wrong way, or something other is happening. We simply have no way of looking. Or on this very active stars, the magnetic field will blocking the events to start. So that's also possible. So what we need is actually gather more observations, obviously, it's always, to see if that's the case. We still need to find the missing solar CMEs because, but up to this point of the presentation, well, there is none. And we need to go for other wavelengths as well, because that the X-ray observation that I showed in the introduction is basically the only example where you can follow the CME actually leaving the star. Because in the X-ray, when you get each photon, it has a time signature and an energy signature. Well, because there are so few photons, you can basically do either photometry or spectroscopy based on your intentions and needs. So if you have enough photons, you can make a nice spectrum, what they call it. And you can see that the CME is seen at first lower atmospheric regions and then at upper atmospheric regions in the spectrum, so in time. But that's the only case. In the case of optical spectra, you are happy to see something moving sometimes. We found that successful CMEs are relatively rare. So basically 90 to 98% of the events are unsuccessful, so below the escape velocity. So they come up and fall back. We see many such events on the sun as well. So if we are focused on life and finding habitable zone planets, then just from this point of view, we could say that CMEs pose a much smaller threat than we thought previously. So initially, people thought that CMEs were one of the strongest danger for habitability because all the particles that would raise the planetary atmospheres. So from this small part of research, it might be possible that flares would be much more serious threat. How could we continue? So there is one problem with looking at the archives, is that when those people were proposing for the observations, they had different scientific ideas in their mind. So maybe they wanted to do Doppler imaging, xenon Doppler imaging, meaning that they wanted to sample the stellar surface different time. And in our case, what we would need is continuous observations, basically day and night. That would be the optimal. Because if you just take one spectrum, you wait half a day and then another, then you don't know that if you see something, is it a noise, just some accident, or a real signal? If it's a real signal, what happened before, what happened afterwards? So looking at the archive is not the best way, actually. We could look at open clusters, and nearby and open clusters seem to be like a good candidate because, well, it's nearby. We might have good signal to noise ratio. There is lots of young stars at a relatively small area. So it seems like a good idea. It has been tried by other people. It has been tried by us. Well, until now, there is no luck with that. So with recently 10 days of observations of the created and planned clusters, we found basically nothing. Maybe we have to get deeper in the data, but the first look seems very unpromising. But there are some other groups dealing with this question as well. The group in Japan has access to relatively large telescopes, so 2-meter and 4-meter telescopes with mid and high resolution spectrographs, and they are basically spending insane observation times on these projects. So they are just popping out papers and papers on CMEs on different stars, and well, if you spend observing time on a random event, then sometimes you get lucky. And they found one of the very rare events on EK Beacons, which is basically a solar-like star. So that's the first detection of a CME on a solar-like star, which is not the sun, which is fun. We could check the sun if we can find solar-like events on it. There are some projects that observe the sun with high-resolution spectra as a star. So one of them is the IAASARS that has a tiny telescope attached to it, which observes basically the sun all the time when the sky is clear and they can do observations. The first data release happened a few years ago. It contains 5 years. The unlucky part is that these 5 years happened during solar minimum, so no big events back there. And the first look at the data is not really convincing. So you can see here that this spectrum here is during a CME, and this is during non-CME. And if you find the difference between the two, can you see any difference? Yeah, because there is basically none. Or if there is any difference, that it will be happening in the telluric lines like this one. So water vapor is changing. The sun went a bit down, and we see more air signal in the spectrum. So it's quite unlucky. And as far as I know, there have been different experiments with this kind of data and trying to find the signal of Jupiter and stuff like that. But they are also struggling. But there have been some claims to find strong flares at least. So there might be some hope to find CMEs as well. That's for the future. So let's go for the second part, flares as data. It's a different. So from spectroscopy, we go for photometry. You probably know that Kepler and TESS are space telescopes that so Kepler is focusing or was focusing on a small spot on the sky and observing something like 100,000 stars for several years, while TESS is basically taking months long of observation sectors and scanning the whole sky. So the question is, can we use these data to find flares? Well, the obvious answer is yes. But how? So if there is 100,000 stars or a million stars, you don't want to go through that manually because you will probably die before finishing. And if you hire PhD students, they'll commit suicide before finishing or resign and move to some other field. So that's not very efficient. They're spending your time or money, or time and money. So you probably want to do some automated method. And there are many ways of finding flares. One is ours. So the basic idea for the simple methods is that you basically try to find the parts of the light curve that don't have flares, remove that from the light curve, and whatever is left is the flare. So that's the simple way, but it's obviously never that simple because all the outliers are sometimes not obvious. There are some light curves that look like flaring light curves, like Lyrae pulsating stars that confuse very often the shadow detection codes. So we wanted to create a machine learning algorithm that basically deals all with these issues by itself. And we just have to press enter and we have a nice table of flares that we can use for science. And we manage progress. So we have a code that detects the strongest flares with high accuracy. I don't claim that it detects all the flares because that's not true. So some of the events are being missed. There are some incorrect detections on weirdly behaving stars. So that's something that, well, that happens all the time. There are some few point false positives that can be easily dealt with. So if you just manually filter the results, you can get rid of all of these. But the lucky thing is that you can get rid of things like this one. So because the way of machine learning algorithm works, if you teach it that, okay, this is how real flare looks like, but this one, this one, this one, this one, and this one are not real flares, so don't care about those. And it will learn if you give enough amount of data. So if you teach it properly, then it will behave more or less the way you would like it to do. So we searched the first 5 years of test data using the 2-minute sampling lifers, and we're checking the results manually because you shouldn't believe what a machine learning algorithm spits out because that's generally a very bad idea. So by checking the results, we created a catalog of more than 100,000 flares on 14,000 stars, which is not the biggest database, but the biggest database that we plan to actually publish. So there is a few. These two catalogs are larger, but they are not published. This one is known to have many false positives since the publication. So ours is somewhere here, so it's relatively a big one. So what can we learn from this? It's very early stage of the research, so we just finished the data relatively recently. The first results of the statistical magic is that the flare shapes, if you scale them, I mean, from all the stars, you scale them to unity and start to comparing the shapes of the flare, you will find that the flare shapes can be described by relatively small number of principal components, say 5 or 10. And with these, you can reconstruct. So with 20 principal components, you can basically reconstruct most of the features in a flare. So that's good news. Most of the flaring stars are M-dwarfs, so that's no big surprise. So just be careful because if you check the spectral classes, so M-dwarf stars, they start here. So most of the events come from these because we already knew that these are the most active stars on the sky. But there are some surprising exceptions. We knew that there are flares on giant stars, so there are some events here. The issue with that is giant stars are, well, giant, so they are very luminous. And if there is a flare on them, it has to be really, really large to be seen in that brightness. So on a tiny star, if you see something popping up, it's obvious that it's there. And there are some strange events here, which seem like actual ones. We don't understand what this could be, so that's for the future. There are some interesting events here as well, in the case of brown dwarfs. So what happens if you start to decrease the size of the stars? So in first, you have solar-like composition, so you have radiative core and the convective envelope, like on the sun. Then around 0.3 solar masses, we will end up with a fully convective star. If you go even, but that's still capable of having a magnetic field a different way. If you go down to the pale cores, so to the substellar regime, if you read older papers. These are not supposed to have coronae like the stars. They are not supposed to have magnetic fields. But seemingly there are some ground bores that don't read those papers or don't care about them. And some of these have flares in H alpha. Some of these are showing radio emission, X-ray emission, like some of them. It's not really clear why, so that's a surprise for the future. And you can see that some of them are really showing flares, so that's something interesting for the future. If you put all the data that we found, we find that the flare parameters correlate with the effective temperature. So that's what we find here. So basically, the larger stars have larger flares. So it's no big surprise. I mean, you have brighter objects, it's expected to have maybe larger, and it's easier to find it as well. But the interesting part that the flare shapes are different a little bit. So what we are speaking about this here. So the difference between the blackish, reddish line and the yellowish line is a little bit different. You zoom in very slowly. It turns out that the hotter stars have slower decay and more complex cooling pattern than cool stars, which is something that we might have expected or not. And it turns out that this was found like a few years before on solar flares, which was published like, okay, this flare is like a flare from an M-dwarf, and this solar flare is like a flare for a K-dwarf. And they compared the two, and because they were much more into plasma physics than we are, they found the correct explanation for that, which we couldn't figure that prior, just possibly because we don't do plasma physics. Yep, so that's the conclusion. And if you have questions, I'm happy to answer them if I can.
There's time for questions. Here to see everyone. Here.
And going back to the beginning of your talk, when you were showing the example of the temperature extraction. So you have the light dominant extraction, after trend stuff. But what is the signature, the spectra, to know that this is a CME?
Yeah, so we have to do the work.
Just to understand why this is.
Yeah, the thing is that I read the paper when it came out. And yeah, I don't remember the details.
Can I ask you something? We are using scaling relations to scale levels to CMEs. And from the possibly, we didn't talk about particles, but at some point you talked about players in CMEs. So we basically assume that when you have CME, right? Which scale relations are you using? If you
Basically, what's happening is that we assume that you have the solar activity, and if you start to increase the rotation speed, you will have so you see more flares because we know that already from stars, and you might see more CMEs. So that's the basic idea, because we don't really see the other details on other stars.
I think I didn't understand that, but if you look over here back. So you have your semi rate per day, and that's your on source time. But you extract this from some kind of scaling relation.
Yeah, but so it's multiple step black magic with many assumptions. So it includes that I think the H alpha is related to H gamma, and then so it's a rather complicated series of solves.
Anyone else? I was wondering, why is there so much data on the archives on these stars, like so many, you said 1,000 hours of spectra? Why do people take it out? You
Yeah.
mentioned a little bit to study the surface.
Yes.
Surprised there's so much that used to be.
So I think most of these come from the CFHD archive, which is the Canada, France, Hawaii telescope, which is one of the biggest archives that's out. And I think they went for the regime of the stars. So to recreate the magnetic field. If you look for the paper of Donati and the group, they have made magnetic reconstructions of, I don't know, dozens of stars at least. So there is a plot called confusogram in conferences, because it has, I think, 6 axes in 2 dimensions, showing the rotation speed, the strength of magnetic field, the axisymmetry of the magnetic field, and lots of other stuff in one single plot. So to create this, they needed to observe lots of stars, and probably I don't know, because that explains only a handful of them. So I didn't check all the science cases that went into these, but this is definitely for the best usable observations which had high resolution spectra.
Yeah.
That's a good mining resource.
So you extracted something else from the spectrum.
And actually, I spoke to the original team, and they said that they had the idea to check the H alpha and the Balmer lines if they contain something, but they decided not to and just focus on the.
I don't see any online either, but let's take our speaker again. Krisztián will be around a little bit for lunch at the QQ, so I got extra questions. Thanks.